Physics 2212, Lab 3, Magnetic Field of Permanent Dipole Magnets. The purpose of this lab was to determine the impact of distance on the magnetic field produced by a bar magnet on and off axis, as well as to compare experimental values to theoretical. We did this by using a magnetometer and recorded magnetic field values at different locations. We used these distance observations to compute the magnetic dipole and glow script code to determine the theoretical magnetic field on and off axis. From this, I determined my results to be the distance dependence equal to negative 2.92 meters and the magnetic moment of the magnet, mu, to be equal to 1.8 amperes times meter squared. In this lab video, I'm first going to go over the main concepts used in the lab, the experimental procedure, the calculations, and glow script code, followed by the discussion questions. The main physics concepts used in this lab was knowing what the magnetic field of a dipole was and utilizing the Biot-Savart law, which is the law that calculates the magnetic field produced by a current, and then using the magnetic field of a bar magnet distance dependence relation, which is shown to the right. For the experimental procedure for the on-axis field, I used the Teslameter app as a magnetometer and calibrated it to the true magnetic north. I then recorded the axis distance needed to get an x component at a magnitude of 20, 70, 120, 170, and 220 microteslas, and did this 3 times at each of the distances and used the averages shown to the right. Using those averages, I was able to produce this plot of the natural log of Bx versus the natural log of R. For the off-axis field, I used the same app and found the perpendicular distance where the magnitude of B net was equal to 100 microteslas. I collected 3 measurements and found the average to determine the off-axis magnetic field shown at the bottom of the screen. During the experiment, I observed that as the magnetometer moved closer to the magnet, the measured x component of the magnetic field increased, and when it moved further from the magnet, it measured a near zero magnetic field in the x direction. In order to do the calculations for the on-axis field, I began by using the plot of the natural log of Bx versus the natural log of R in order to solve for the distance dependence of the magnetic field by utilizing the slope equation. From this equation, I could find that my n was equal to negative 2.92. I was then able to use the natural log of k in order to solve for the magnetic dipole moment by using the relationship that the b of the bar equals to kr raised to n. From this, I found that my magnetic dipole moment, mu, was equal to 1.8 amperes times meter squared. I created a glow script code to both visualize the magnetic field and also to determine my theoretical values. I started by creating a magnet at the origin to represent the magnet using my experiment, and then by creating the magnetic field using a function that was based on the Biot-Savart law. I then moved on to create my arrows. I created 2 arrows on axis and 4 arrows perpendicular to axis. Lastly, I created an arrow at the 45 degrees off axis, and then here you can see my results that I obtained from this code. In one picture you can see the frontwards view, and on the side you can see another view that shows all of the arrows. At the bottom you can see the fields that I determined using the theoretical values. In analyzing my results for the magnetic field at the 45 degree axis at 0.178 meters, I determined that my experimental value was not that different from the theoretical value, except mainly at the z location. So for the discussion questions, I determined that had I not compensated for the magnetic north, the x component of the magnetic field would not have started at 0 teslas, so the final answer would have been the magnetic field of the bar as well as the Earth. The distance dependence would have been different, as well as the magnetic dipole overall would have been different. I also determined that had I sucked 2 magnets together end to end and run the experiment again, the magnetic field would have increased, but the direction of the field would have stayed the same. In conclusion, by using knowledge of magnetic fields as well as the Biot-Savart law, I was able to determine the distance dependence of the magnetic field to be negative 2.92 meters and the magnetic dipole moment to be 1.8 amperes times meter squared. From this experiment, I concluded that the magnitude of a magnet field due to a bar magnet decreases with increasing distance.